Hello everyone, this is Mirzai from Cal Poly Pomona, and in this lesson we are going to learn how to solve a linear programming problem using the Big M method. Big M method is used when there are constraints with greater than or equal signs in a linear programming problem. Before solving a problem using the Big M method, we need to learn the concept of excess and artificial variables. The concept of excess variable is very similar to the slack variables in the simplex method. Let's understand this concept by an example. Suppose we have a maximization problem which is subject to 3 constraints with less than or equal sign and 1 constraint with greater than or equal sign. The first step before solving this problem is to standardize it. For the constraints with less than or equal sign, we earlier learned how to use the slack variables. For the last constraint, however, I cannot use the concept of slack variables because despite the first 3 constraints, it has a greater than or equal sign. Let's see how we can treat this constraint. Consider a feasible solution to this problem. For example, x1 equal to x2 equal to 100 is a feasible solution to this problem because if you replace x1 and x2 in the first constraint, you'll see that this satisfies the first constraint because you get 300 less than 600. Also, if I put it in the second constraint, it satisfies this constraint as well. If I replace it in the third constraint, I get 900 less than 1000, so the constraint is satisfied. If I replace it in the fourth constraint, I get 300 greater than or equal to 150, so the constraint is satisfied. That's why we call this solution a feasible solution to the problem. Now, if I replace this feasible solution to the last constraint of this problem, which has a greater than or equal sign, you'll see that the left-hand side will be 300. Despite the constraints with less than or equal sign that we have to add some amount to the left hand side of the constraint, as you see in this case we have to reduce some amount from the left hand side to make it equal to the right hand side, which is 150. This amount that we reduce from the left hand side is called excess and is shown by E. So E is equal to 150 in this example, which by accident is equal to the right hand side, but it doesn't necessarily have to be equal to your right hand side. It's the amount that you have to reduce from the left hand side to make it equal to the right hand side of the problem. E is related to the fourth constraint, that's why we give it the index of 4. Now, the problem with this standardized form is for this constraint, we don't have any basic variable. According to the definition of a basic variable, it should have the coefficient of 1 in one constraint, and in all the other constraints, its coefficient must be 0. Or in another word, it should only appear in one constraint of the problem, and its coefficient usually must be a positive 1. You might say, if I multiply this equation by a negative 1, then I probably get what I'm looking for. I get a positive coefficient for E4. But if I multiply this equation by a negative 1, I will get a negative 150 for my right hand side, which is an infeasible solution for LP. At the initial table of the simplex, we said we put x1 and x2 equal to 0. I get E4 equal to negative 150, which according to the definition, all the decision variables for a linear programming problem should be positive. So this is an infeasible solution for this problem. To resolve this problem, we introduce artificial variables. Artificial variables are variables that are added to constraints with greater than or equal sign to generate that basic variable that we are looking for to start the problem. In this example, if I add an artificial variable to the left hand side of this problem, I can generate that decision variable that has a coefficient of 1 in one constraint, and all the other coefficients of A4 are 0. You don't see A4 in any of the previous constraints that we have. So now we can start the simplex using this initial solution. But A4 doesn't actually exist. It's an artificial variable that helps solve the problem. It's a sort of auxiliary type of decision variable. So we have to get rid of A4 along the way as we solve the problem. Since we're looking at a maximization problem, if I add this A4 with a very big negative coefficient in the objective function, And then my optimization problem try to minimizes A4 because it has a really big negative coefficient. So its contribution to the objective function is negative, and it's really big. If A4, for example, gets a value of 1, let's say its coefficient is negative 1 million, so negative 1 million, it's a really big amount that will be deducted from my objective function. So what the optimization tried to do is to eliminate the impact of A4, and then we can get rid of this artificial variable along the way, because in the first place it doesn't exist. So what I do, I add A4 with a very big number with a negative sign to the objective function of maximization. Along the way, to maximize this problem, I reduce the value of A4 as much as I can, and hopefully I will reduce A4 to 0. This way I can eliminate the impact of A4 from the objective function. Again, we have to standardize this problem, so we take all the decision variable to the left hand side and make the equation equal to 0. Now the thing that you have to pay attention is adjust your objective function before you standardize it. If you standardize and then add negative MA4, we'll actually try to increase the value of A4, which we are not looking for. If you define auxiliary decision variable A4 for your problem, then your objective function have to reduce that impact. So if you're looking at a maximization problem, we add a very big number with a minus sign to the objective function, whereas if I'm looking at to a minimization problem, I will add A4 with a very big coefficient to the objective function. So and the sign of M here depends to the direction of objective function. For maximization is negative, for minimization is positive. But the logic is the same. Alright, we have set up the initial table of simplex and we are good to start. Again, all the steps are very similar to the regular simplex method, where we are looking for the most negative value in the row of Z, and then we're trying to run the minimum test to find the exiting decision variable. However, before we start solving the problem, we have to do some manipulation in the row of Z. If you look at this table, A4 is a basic variable and has a coefficient of M in the objective function, whereas according to the definition it should have the value of 0, and anything besides this value in this column should be 0. So now we have to do some manipulation in this row to make that change happen, to change that M to 0. To be able to do this, we have to again use the elementary row operation. The elementary row operation that we introduce in this step is negative M multiplied by the fourth row of the table plus the row of Z. Why I choose the fourth row of this table? Because if I multiply this row by negative M and then add it with the row of Z, I'm able to generate that 0. Whereas if I use any of other rows that we have, it doesn't change anything because the coefficients here are 0. So anything I multiply by these rows doesn't have any impact. So the only option that we have is the fourth row, and I use this row to manipulate the row of Z. Here you're able to see the new row of Z. Now we can start the simplex method very similar to what we have done for the regular simplex. So if I look at the most negative value in the row of Z, this is the most negative number. M is a very huge number. You can always replace that M with a big number, let's say 10 to the power of 6, if that makes it easier for you to understand. Now to find what is the decision variable that will exit the basis in the next table, we have to run the minimum test. If I do the minimum test, which is dividing the right hand side of your problem by the positive value of your pivot column, you'll see that the minimum number is related to the fourth row of this table. So the pivot row will be the fourth row, and the intersection of the pivot column and pivot row gives you the pivot value, which is 2, and in the next table we have to change that value to a value of 1. And also in the next table, x2 will replace a4. So the decision variable related to the pivot column will replace the decision variable related to the pivot row. So x2 replaces a4 in the next table. But all the other decision variables are the same. Now, the elementary row operation to change the pivot row to a value of 1 is dividing the pivot row by 2. So R4 divided by 2 is the elementary row operation we need to do. Now we have to use this row to manipulate the other 3 rows to have value of 0 in the pivot column. Now, by elementary row operation of negative R4 plus R1, we are able to generate 0 in the first row. If you have forgotten about the elementary row operations, please refer to the lesson related to elementary row operations. And if I multiply the 4th row of this table by negative 1 and adding it with this row, the first row here, we're able to generate the value of 0 here. Now let's do this operation and see how the first row will change. As you see, we are able to generate the value of 0 here. The elementary row operation to change the second element of the pivot column to 0 is negative R4 in the new table, or our new pivot row, plus the second row in the old table. Similarly, to change the third row of the pivot column to a value of 0, the elementary row operation will be negative 2 multiplied by the 4th row of the old table plus the 3rd row in the old table. Now remember, we have to always have a pivot row used in our elementary row operation. It doesn't matter whether we are using the pivot row in the new table or in the old table. So in this example, instead of multiplying this row by negative 4, I decided to multiply this row by negative 2. You can use either one, pivot row in the new table or a pivot row in an old table to set up your elementary row operation. Make sure that you always multiply a pivot row by some amount and then add it with a row that you want to see the change in it. By doing this, I get the new third row of simplex table. Now the last part is to define elementary row operation for changing the element of the 0 in the pivot column to a value of 0. The elementary row operation will be 2m plus 4 multiplied by the new pivot row plus the row of z. Again, as you see, I defined some coefficient for the pivot row in the new table and added with the row that I want to see the change in it. So if you pay attention to these elementary row operations, you see what is in common between all of them. You see that this is a row that we are changing every time, this part, and the first part is pivot row multiplied by some number. So every time you're trying to find what should be the coefficient of pivot row, where when you add it with the row that you want to see the change in it, you're able to see that change. Now if I implement this elementary row operation, I'm able to see the new row of z, which has a value of 0, and there x2, which is our new basic variable. Now x2 has become a basic variable in this new table, and if I look at the column related to x2, I see 1 for x2 and x2, and all the other elements are 0 in this column. So that kind of confirms that I was able to make x2 a basic variable. For all the basic variables, you should see the same pattern. If I look at the s2 column, I should only see 1 in one row, and all the other elements should be equal to 0. Now we have to check for optimality condition to decide whether I have to continue or stop the simplex. For a maximization problem, optimality condition is when all the coefficient in the row of z are positive. But here we see two negative values, which are negative 1 and negative 2. So we have to continue the table of simplex. Again, I have to look for the most negative value here and implement the minimum test. As you know, we implement the minimum test only on the positive value of pivot column, which are 1/2, 1/2, and 2. By implementing the minimum test, you see that the minimum value is related to the second row of this matrix. So we have to change 1/2 to a value of 1 in the next table, because E4 is going to replace S2 in the next table. So if I do this replacement, the elementary row operation to change 1/2 to 1 is to multiply this row by a value of 2, and this is the new row that we get. Now we have to use this row to manipulate other elements of the pivot column to become 0. To change the first row element in the pivot column to a value of 0, if I multiply this row by a -1 and then add it with the first row here, I'm able to see the value of 0 that I was looking for. So that's what I'm going to implement in here, which is -R2 in the old table plus R1 in the old table. To change the third row of pivot column to a value of 0, we multiply the second row of the new table, which is our pivot row, by -2 and then add it with the third row in our old table. So implementing this step gives us the new third row in the next table. Now, since this one is -1/2 and our pivot row has 1/2, by implementing this step, we're going to get the new fourth row, which gives us a value of 1 for E4, and all the other values are 0 in this column. Now we have to also manipulate the row of Z to have a value of 0 for this element here. So if I multiply the second row, which is my pivot row, by a value of 2 and then add it with the row of Z, I'm able to generate a value of 0 here. Let's do this operation and see how it works. 2 multiplied by the second row of the new table, which is my pivot row, plus this row of Z, it will give me the new row of Z. Now again, if I look at the pattern, as you see, every time I multiply something with the pivot row and then add it with the row that I want to see the change in it. Now I have to check for optimality condition here to see whether I have to stop, I'm in the optimal table, or I have to continue. As you see, all the elements here are positive, so for maximization, when we have everything positive, we are at the optimal table of the simplex. So do I have a final solution to this problem? Before deciding about the final solution of this problem, you have to check whether you see an artificial variable in the basis of your table or not. If you see an artificial variable here, your optimization problem doesn't have a feasible solution, because we know that the artificial variable doesn't exist. We want that artificial variable to become 0. But here, since we do not see any artificial variable, we are at the optimal solution. So in the optimal table, the artificial variable is not a basic variable. Thus, the optimal solution is a feasible solution. Otherwise, we couldn't conclude that we have a feasible solution to this problem. And not only we have a feasible solution, but also we have optimal feasible solution, because we reached the final table where all the values are positive in the row of Z. Your final Z value is 900. All the other decision variables that I don't see in the basis are equal to 0. And the decision variables that I don't see here are x1, s2, and a4. So the value related to those are equal to 0. With this, our lesson in Big M is concluded. Please refer to your Blackboard for your assignments. Thank you.